So, good evening, everyone, and welcome back to this problem solving session for the NPTEL course Geology and Soil Mechanics. So, those were new for today's session. So, for them, I am Shivshankar Nandi. So, I am TA, one of the TAs of this course, and I will be taking this problem solving session on every Sunday from 5 p.m. to 7 p.m. So, with this brief introduction, we'll start today's session. So, in the previous week, we have basically learned about the engineering geology of soils and their formation and different index properties of soils like this three-phase relationship, water content, void ratio, then degree of saturation, relative density, consistency of soil, so on. So these are the different terms which terminologies which we have learned under the heading of index properties of soils. Now, in this week, that is in week 2, we have proceeded further and we have learned about the classification of soils and clay mineralogy. So these are the again two very important aspects in soil mechanics. So as a geotechnical engineer, so we should have a very thorough background or basic understanding of these topics. Okay, so classification of soils and clay mineralogy. So you must be aware with this fact that classification of soils, why this is needed and how a soil can be classified. So for classification of soils, there are various systems or classification systems are available in the literature or even in many standard textbooks. So we can name a few of those classification systems like unified soil classification system. Okay, so I am writing here the abbreviation of those classification systems. So the first one we can refer the USCS. Okay, so this is nothing but the Unified Soil Classification System. Now coming to the second one, there is another classification system which is called ASTO. Okay, American Association of State Highways and Transportation Officials, ASTO. And third, the Indian Standard Soil Classification System. Now, as per the scope of this course is concerned, so we'll be learning about only about the Indian Standard Soil Classification System. That means according to Indian Standard Soil Classification System, how a given soil can be classified. Okay, so we have seen that the classification basically begin by classifying the soil into two categories like coarse grained and fine grained soil. Now, if the soil is coarse grained, then it will be classified on the basis of its grain and gradation characteristics. Whereas in the case of fine grained soil, the soil would be classified based on its plasticity characteristics. So we'll see in details how a soil can be classified depending on these aspects in today's session through a few selective numerical problems. Okay, and secondly, we have learned about the soil structure. So whether it is dispersed or flocculated. So means if you go through the lecture content or lecture materials which are uploaded in the course website, so you can see that when the soil particles basically approach uh, to each other. Now, if the net energy of the system if the net energy of the system is seen to reduce, then a specific type of structure will be formed. And if that is not the case, means if the net energy of the system is seen to be increased, then another kind of structure will be formed. Okay, so that you can learn from or you can check it from the lecture contents or lecture materials. And lastly, we have learned about clay mineralogy. So we have seen different clay groups, mineral groups like kaolinite, montmorillonite, illite. Now, what is the means atomic structure of this kind of group? Which is what is the thickness of this group? Means this clay mineral. Then their sensitivity in the sense means some particular group of clay mineral is basically highly sensitive to water. Means water can easily enter into the crystal structure of that clay mineral, and in that way it's very sensitive to a volume change. Okay, so all these aspects are basically covered under this heading called clay mineral and clay mineralogy. And this topic is also very essential for a thorough understanding of soils which contain these mineral groups. Okay, so with this we'll uh, move on to the problem solving part of this session. So as you know that in the last week we started solving a problem which is based on, or which is basically uh, framed on the basis of sieve analysis and hydrometer analysis, and we couldn't solve the problem entirely in that session due to lack of knowledge. Means by that time we don't know about, or we didn't know about the soil classification system, so that we restrained ourselves only for the only to the calculation procedure. Now in this session we'll again start that problem by classifying the soil. Okay, so before that we'll read the problem statement once. So the problem states that 500 gram of soil taken from Kanpur, Uttar Pradesh were brought to a soil lab for testing of grain size distribution. The weight and number of each sieve for sieve analysis is given in table 1. So in table 1, two columns are there. So in the first column, sieve size, which are the size of sieves which are used in the analysis is given, and in the second column the corresponding sieve weight is also given. Okay, now after the sieve analysis, the weight of each sieve along with the soil is given in table 2. It is to be noted here that during sieving, a small fraction of the sample taken was lost as dust. Okay, so in addition to table 1, in table 2, the sieve plus the retained soil weight. Okay, weight of sieve and the retained soil is given corresponding to each sieve size, starting from 4.75 mm to 0.075 mm. Okay, and it is explicitly mentioned in the problem statement that while the sieving operation was done, a small fraction of the sample which was earlier taken, that is 500 gram. So out of that 500 gram, a small fraction was basically lost as dust. Okay, that we have to keep in mind. Now coming to the hydrometer analysis part. So a hydrometer analysis was performed on the same soil by taking 40 gram of the sample retained in pen. So this is the standard procedure. As you know that this hydrometer analysis is primarily performed for fine content, okay, for the finer portion or finer fraction of the soil. So there are two different methods. So the first one is sieve analysis, as we have seen, and the second one is this hydrometer part. So sieve analysis is basically performed for the coarser fraction of the soil, and hydrometer analysis is basically performed for the finer fraction. Finer in the sense the portion which has passed through the 75 micron sieve. So in that way, the soil which is basically retained in the pan, now out of this soil 40 gram was taken for hydrometer analysis. The hydrometer immersed in a soil solution of 1000 ml was read at specific timings as given in table 3. So these are the readings obtained from the hydrometer analysis. It is basically summarized in table 3. Okay, so in this specific context, so we have discussed about two very important factors, or important facts, that to proceed further for hydrometer analysis, means to proceed for the calculation part which is involved for the hydrometer analysis, we have to first calibrate the hydrometer. Calibration in the sense we have to first establish a relationship between hydrometer reading and the effective depth. Okay, that we'll see. And next, this in the calibration part itself, we have to basically implement some hydrometer corrections. Okay, so whatever we have got, this RH or reading, that is basically raw reading. Okay, so we have to basically implement some corrections. So these are the different types of corrections which are basically valid for hydrometer. The first one is meniscus, then the second one is temperature correction, and the third one is dispersing agent correction. So this relationship between hydrometer reading and the effective depth, so it is basically between, actually in the sense of corrected hydrometer reading. So after implementing the correction, you have to calibrate the hydrometer. Okay. Okay, and these are the some statements or data which are also given corresponding to the hydrometer analysis part, and using this data you can determine the diameter of particle which basically falls through a specific height or effective depth, and the corresponding percentage finer. Okay, so the calibrations correspond to 3 as 20 centimeter and 24 as 7.5 centimeter effective depth. So this statement is very essential for establishing the relationship between the effective depth and the hydrometer reading. Then the viscosity of water is given 8.9 into 10 to the power minus 7 kilonewton second per meter square. The soil solution temperature was at 32 degrees centigrade. The meniscus correction is 0.5, and the combined dispersing agent and temperature corrections was observed to be minus 2.1 for the hydrometer. Specific gravity of soil particles was found out to be 2.67 from experiment, and the formula for diameter and percentage finer for hydrometer analysis is given below. Okay, so you have to use this formula. So these formulas are nothing but derived based on the Stokes law. Okay, so if you are not aware or if you are not basically accustomed with this equation, so please go through, I will request you that please go through the lecture material so you can basically easily get or check into about this equation, so how these equations are derived. Okay, so at least for the exam purpose you need to know about, or you need to worry about the final results. Okay, so what is the final outcomes of the derivation, so that you have to basically keep in mind. And in this way these two equations are put in this slide so that you can easily uh, basically perform the analysis or the calculation part. Now, based on all this data, we have to answer the first question was what type of soil is it? And secondly, according to the coefficient of curvature and coefficient of uniformity, the soil can be classified as. Okay, so these are the two questions which we didn't address in the last class because at that time we didn't cover the classification aspect. Okay, classification of soil, so that we discuss that we'll answer these two questions in the next session. Okay, so that means in today's session we'll address these two questions. Now before addressing, so this is the table which we have basically completed corresponding to the sieve analysis part. So I am going through very briefly. Okay, so since it was already done in the last class, so corresponding to each sieve size we have basically determined the percentage finer, and it's a very straightforward. Okay, so and this in this table we have calculated both this d in millimeter and the percentage finer on the total basis. Okay, so this d and percentage finer n, so these are basically calculated using these two equations. So equation, if I rename these two equations, then equation 1 and equation 2. So in this table, so d is basically obtained from equation 1, and this one percentage finer n, so this is obtained from equation 2, and we have to basically correct this percentage finer. Why this correction is needed to get the percentage finer on total? Because we have explained that whatever percentage finer corresponding to our diameter d we are getting in this column, that is the second last column of this table, that is on the basis of or with respect to 40 gram of the sample retained in pan. However, we have to get or we have to obtain the percentage finer on the total basis. Otherwise, we cannot complete the total or the final grain size distribution curve. The main motto of this problem is to obtain the grain size distribution curve, and depending on that we can make a note whether the soil is well graded, gap graded, or poorly graded, something like that. Okay, so that is the question 1b of this problem. So that's why we have basically made one correction to get the percentage finer on the total basis. And how? So in this way, so this is the percentage finer. This is with respect to the 40 gram which we have taken. Now this is the fine content. Okay, 21.96. 21.96, how we have got? So in this way, so 21.96, this is basically this much fraction percentage is passing through 75 micron sieve. Now uh, out of this 21.96 percentage, we have taken 40 grams. So in this way, we have multiplied this 21.96 to get on the total basis. Okay, out of 500 gram, how much percentage fine means how much percentage finer is corresponding to 0.052 millimeter dia particle. Okay, so in this way, we have got 19.66 to 2.37 corresponding to the particle size of 0.052 to 0.001. Okay, so this is the slide related to the hydrometer corrections. So this is the corrected hydrometer reading. So it is basically uh, written as the raw hydrometer reading plus cm plus minus ct minus cd. So that basically depends on the nature of the correction. Means meniscus correction is always positive, temperature corrections can be positive, negative depending on the test temperature, and dispersing agent correction is always negative. Okay, so depending on that, we have got the final expression or the final relationship between the raw hydrometer reading and the corrected hydrometer reading. And this is related to the calibration of the hydrometer. Okay, so initially some data were given. So the means this hydrometer reading and the corresponding effective depth was given. Now depending on this relationship, we can extend or we can interpolate the actual hydrometer reading or the corrected reading, that is for time t equals to 0.5 minutes, the corrected reading which we have got, that is 22.4. Now this 22.4 hydrometer reading represents what effective depth? So that we can get from this calibration. Okay, so if the hydrometer reading is 22.4, then what should be the effective depth? The effective depth should be 8.45 centimeter. How we have got this? We have got this on the basis of calibration of the hydrometer. Okay, now this is the final table. Now in this table, basically first column dictates about the particle size and the second column dictates about the percentage finer, corresponding percentage finer. Now this data x and y, these two data were basically plotted in a semi logarithmic plot. Now in that plot, basically y axis dictates the percentage finer in the arithmetic scale, and the x axis represents the diameter of particle in millimeter in the logarithmic scale. So that's why it's called a semi logarithmic plot. Okay, now after plotting these data points, we have basically joined these data points by a smoothly these data points by a curve, and the curve which we have obtained, it is nothing but the grain size distribution curve. Okay, and for obtaining this grain distribution curve, we have basically utilized the data obtained from both the sieve analysis and the hydrometer analysis. So sieve analysis portion is from 4.75 millimeter to up to 0.075 millimeter, and hydrometer analysis data that is basically beginning from 0.052 millimeter to 0.001 millimeter. Okay, so we have basically considered the data obtained from both the experiments, sieve and the hydrometer analysis, and then we have plotted this data in a semi-logarithmic plot, and we join this data by a smooth curve, and whatever we have obtained, that is called grain size distribution curve. So this was the task in the last class. Now we'll proceed further. So we'll proceed further to classify the given soil sample. Now before that, what we have to do, we have to first, as you know, that the classification The first or the fundamental step in this ISSCS soil classification system is to categorize the soil sample or the classify the soil sample whether it's fine grained or coarse grained. Okay, so for that what we'll do, we'll basically first make a division of soil fraction on the basis of grain size. Okay, so division of soil fraction on the basis of grain size. Okay, now as you know that this is 300 mm, this is suppose 4.75 mm, this is suppose 0.075 mm, and this is suppose 0.002 mm. I am mentioning here very carefully that this scale, okay, so this distinction is not drawn or is not basically made as per the actual scale. Okay, now this 4.75 to 300 millimeter, okay, we can again make a distinction here. So 80 mm suppose, then so this 4.75, the particles which are in the range, the particles of size ranging in between 4.75 mm to 80 mm, so this is called gravel. Then the particle of size ranging in between 0.075 mm to 4.75 mm, it's called sand. Particles of size ranging in between 0.02 mm to 0.075 mm, this is called silt. And all the particles which are having a size or diameter less than 0.02, okay, so if we extend this line further, so less than 0.02 mm, this falls under the category of clay. And this division 80 mm to 300 mm, so this is rubble, and greater than 300 mm, this is called boulder. Okay, now again we can basically subcategorize the this division, each of this division specifically for 4.75 to 0.075, we can make a distinction like that. it's a coarse sand or medium sand or fine sand, okay, like that. And similarly, the gravel can be also categorized under two, can be categorized into two different parts, coarse gravel or fine gravel. Okay, so we are not going into that aspect because that is not needed at all, at least for solving this particular problem one. So our first job would be to determine the soil fraction on the basis of this grain size. Okay, so we'll basically calculate in this fashion, that this is the particle size in millimeter, and this is the percentage by weight. Now, as you can see from this table, that 98.88% of the total soil passes through 4.75 mmc. Therefore, the particles which are having a size greater than 4.75 mm is only 100 minus 98.88, that means 1.12 percentage. Okay, so out of 500 gram soil sample which was originally taken from the site, now only 1.12 percentage soils are having a particle size greater than 4.75 mm diameter. So similarly, we can calculate the percentage by weight for the particle size 4.75 mm to 0.075, and this is nothing but the sand fraction. Okay, so this is nothing but the sand fraction, and this is roughly we can say gravel. Now, what is the sand percentage in the soil? So, sand percentage, this is basically confined by these two ranges, 0.075 mm to 4.75 mm. So, the particles which are having a diameter ranging from 0.075 mm to 4.75 mm, that are called sand. So, that would be so 21.96 percentage passes through 0.075 millimeter dia or millimeter sieve, and 98.88 percentage passes through 4.75. So the subtraction or the difference between these two values would give you the percentage of sand inside the given soil mass. Okay, so that means 98.88 minus 21.96. So the value would be 76.92. 76.92. So this much percentage of sand is in the given soil sample. Okay. Now we'll calculate the silt fraction. Silt fraction means the particles which are having a size ranging from 0.02 to 002 to 0.075. Okay, so we are basically writing the size in the decreasing order. Okay, so this fraction is called silt. So again, we can calculate this fraction by subtracting by subtracting 4.56. Okay, so 4.56, because 4.56 percentage passes through 2 micron, and 19.66 passes through, sorry, not 19.66, 21.96 passes through 75 micron. So 21.96 minus 4.56, that will give you the seal fraction. So how much it is? So 21.96 minus 4.56, this is 17.4. And finally, the fraction which is having a particle size less than 0.002 millimeter, that is 2 micron, that is called clay. And what is the percentage? That is simply 4.56. Why? Because 4.56 percentage passes through 2 micron sieve. So that means 4.56 percentage of the total soil is finer than 2 micron. So that will basically constitute the part of clay fraction. Okay. Now in this way, we have got the percentages of different soil fractions, means gravel, sand, silt, clay in the given soil sample. Now if you add all these fractions, means starting from gravel to clay, means 1.12, 76.92, 17.4 and 4.56, you will be ending up with 100%. Okay, so that's a rough check whether you are approaching in the correct way or not. Now what we will do, we'll check. Now the first check is whether 50% of the total soil is passing through 75 micron sieve or not. Okay, so this is the first check. Depending on that, we'll be categorizing the given soil as fine or coarse grain, whether it is fine grain or coarse grain. Now as you can see, 21.96, only 21.96 percentage of the total soil is passing through 75 micron sieve. That means more than 50% is retained or is coarser than 75 micron sieve. So this indicates the given soil sample is coarse grain, not fine grain. So how we are categorizing the given soil sample as coarse grain? Because more than 50%, more than 50% of the soil of the given soil retained on 0.07 mmc. Okay, so we can infer from this observation that the given soil sample is coarse grained in nature. Now what we'll do, we'll again subclassify. So this is the second check. Okay, so we'll again subclassify the soil sample. So first we have classified the given soil sample as coarse grain on the basis that more than 50% of the given soil retained on 75 micron sieve. On that basis, we have classified the given soil sample as coarse grain. Now we'll again subclassify the soil sample. How? So we'll check whether this coarse grain, the coarser fraction, out of this coarser fraction, how much percentage is retained on 4.75 mm sieve or you can indirectly say how much percentage of this coarse grain fraction is passing through 4.75 mmC. So on that basis, you can subclassify the soil sample as sand fraction or gravel fraction. So here in this table, I have written na. So this coarse fraction. So these are the coarse fraction. So these are the coarse fractions, and these two are the fine fractions. Okay. Now, what is the coarse fractions? The coarse fractions is 76.92 plus 1.12. That means 78.04. 78.04 percentage. Obviously, the remaining 100 minus 78.04 will be the fine fraction. 21.96. So the soil is coarse grain. Now out of this 78.04, how much percentage is retained on 4.75 millimeter sieve? Only 1.12 percentage. Please keep in mind, only 1.12 percentage is retained out of this 78.04 on the 4.75 sieve. Now on a percentage basis, if the coarse grain soil sample, if we take this 78.04 as 100%, then we can easily say that more than 50% of the coarse fractions is passing through 4.75 millimeter sieve, which indicates the sample is in sand. Okay, is sandy in nature. So we are writing down here the second observation which we have got on the basis of second check, that is more than 50% of the coarse fraction in the sense the particles which are coarser than 0.075 mm. Okay, so here I am writing 0.075 mm passes through 4.75 mm sieve. Therefore, the soil is sand. Okay, the soil is sand. So first we have classified the soil sample as coarse grain. Then in the second step we have classified the soil sample as sand. Now we'll further classify the soil sample on the basis of fine content. Now once the soil is classified as coarse grained or fine grained, depending on that we'll basically decide the next criteria. Okay, so on what basis we can further classify the given soil sample. Now as you know that for a coarse grained soil, gradation and the grain characteristics will be predominant. Okay, and for fine grained soil the plasticity characteristics will be the predominant. So for coarse grained soil you have to classify the soil on the basis of its grain and gradation characteristics, whereas for fine grained soil you have to classify the soil sample on the basis of its plasticity characteristics. Now for the given problem, as the soil is coarse grained, and more specifically we can say that the soil is sandy in nature, so we have to go for by its grain or gradation characteristics. Okay, now before that again we have to make a check Okay, whether the fine content is less than 5% or is in the range of 5 to 12% or more than 12%. Okay, so these are the three checks for further classification of the given soil sample. 5%, 5 to 12% and more than 12%. Now, if the fine content is less than 5%, then you have to classify the soil sample as whether it is a well-graded sand or poorly graded sand or well-graded gravel or poorly graded gravel. Now, for the given problems, since the soil is sandy in nature, so you have to basically apply either poorly graded sand or the well graded sand. Okay, why? Oh, sorry, only for the case when the fine content is less than 5%. But this is not the case here. You can easily observe the fine content. Now, what does it represent by fine content? So, the fine content is the fraction of the total soil which is basically passing through 75 micron sieve. So, in that sense, the fine content for this problem is 21.96 percentage. Okay, so fine content, so this is 21.96. The soil is having 21.96 percentage fine content. So it's not less than 5%. If it is less than 5%, then what I have said just now, that you have to go for only the gradation characteristics, well graded or poorly graded. 5 to 12, then you have to use dual symbol. However, this is the third case, that is the fine content is greater than 12%. So you have to further classify the soil sample on the basis of plasticity chart. How? That we'll see. So you have to know the plastic limit and liquid limit of the soil, and you have to calculate its plasticity index. Then you have to plot the soil in the plasticity chart, and you have to identify whether given soil is plotted above the A line or below the A line. If it is plotted above A line, then the fine content will be clayey in nature. If that is not the case, then the fine content will be silty in nature. Okay, however, roughly we can say, because as you can see from this table, that out of this 21.96 fine content, 17.4 percentage, the silt percentage is 17.4, whether the clay percentage is 4.56. So very nominal, the clay percentage is very nominal. Therefore, at this moment you can say that the soil is silty sand. The soil is silty sand. Okay, so here I am writing that the silt percentage, so this is the valid case for this problem. I am highlighting. Okay, and again I am writing that percentage silt is greater than percentage clay. So this is 4.56 and the silt percentage is 17.4. So roughly we can say that the soil is silty sand. And what would be the group symbol for this type of soil? The group symbol would be SA. The prefix S indicates sand and the suffix M indicates silt. Okay, so the soil is silty sand. So this is the correct option. Option 3, this is the correct answer. So what type of soil is it? The soil is silty sand. Okay. So that means option 3 is the correct answer. But this is an approximate, this is basically made, this note is made on an approximate basis. Okay, so we'll again utilize the data given in problem 2, that is in this next problem, and we'll make basically more specific classification or thorough classification of the given soil sample on the basis of plasticity chart, whether the given soil is plotted above a line or below a line. Okay, so that will give you a clear view of the given soil sample. Now this is now for this part the data of problem 2 is required, so that we'll see later. But before that, we'll address the second question, that is, according to the coefficient of curvature and coefficient of uniformity, the soil can be classified as well graded, uniformly graded, gap graded, or difficult to say from the given data. So we'll concentrate on this aspect now. Okay, so this is the grain size curve. Now you have to make a statement on the gradation characteristics of the given soil on the basis of two constants, the uniformity coefficient, the coefficient of uniformity, that is Cu, and this is the ratio of D60 by D10. Okay, and the coefficient of curvature, that is represented as D30 square divided by D60 into D10. Now what are these D60, D10, D30? What are these D60, D10 and D30? Okay, so these are nothing but the particle size corresponding to 10% finer, 30% finer and 60% finer respectively. Okay, so if we denote this D60, D10 and D30 in this grain size distribution curve, then you can draw a horizontal line from 60% finer. Okay, so from the value of 60% finer, you can draw a horizontal line, and the line intersects the grain size distribution curve at this point. Okay, so the particle size corresponding to this intersection point would give you the D60 value. Similarly, a horizontal line drawn from 30% finer would intersect the grain size distribution curve at this point, and the grain size distribution and the particle size corresponding. Okay, so it will be better if I can rename these points as 1, 2 and 3. Okay, so suppose this is point 1, this is point 2 and this is point 3. So the abscissa of point 1 would give you D60, abscissa of point 2 would give you D30, and abscissa of point 3 would give you D10. And how we have got these points? By extending a horizontal line from the corresponding percentage finer and making an intersection with the drawn grain size distribution curve. Okay, so from 60% finer, we have basically drawn a horizontal line, and this line intersects the grain size distribution curve at a point, and particle size corresponding or abscissa corresponding to this intersection point would give you the D60 value. Okay, so I am mentioning here, so this is D60, this is D30 and this is D10. Now From this plot, we can get this value as, so D60, so this value would be in between 0.1 mm to 1 mm. Okay, so this is 0.1, 0.2. In this way, you have to rate this x-axis. So 0.1, since this is in logarithmic scale, so 0.1, 0.2, 0.3, 0.4, 0.5. So the D60 value in between 0.4 to 0.5, and more specifically the D60 value you can take as 0.58 mm. In the similar fashion, you can get the D30 value in between 0.1 and 0.2, and you can approximately take this value as 0.12. And D10, it's having a value in between 0.01 to 0.02. So we can take it as 0.016 mm. So these values we have got from the grain size distribution curve. So you can realize why this kind of grain size distribution curve is very, very essential for the soil classification, for classifying a given soil. Okay. Now we'll calculate this value Cu and Cc. So Cu, this would be 0.58 by 0.016. Okay, so 0.58 by 0.016, this is 36.25. And Cc, D30 square, that means 0.12 square divided by 0.58 into 0.01. So that means 1.55. Now, what is the criteria, or what are the criteria based on which we can basically make a comment on its gradation properties or gradation characteristics, whether the soil is well graded, gap graded, or poorly graded? What is that criteria? So since the soil sample is sand, so for sand, if the Cu value is greater than 6, if the Cu value is greater than 6, we can say, if the Cu value is greater than 6 and if the Cc value is in between 1 to 3, okay, so it's in between 1 and 3. So if these two conditions are fulfilled, then you can say that the given soil is well graded. Okay. Now, without this calculating these two parameters, that is the coefficient of uniformity and coefficient of curvature, again you can classify or you can make a comment on its gradation characteristics only by observing the grain size distribution curve. Okay, so as you can see, the present grain size distribution curve, this covers the particles having size over a broader range. Okay, so the given soil sample is the having particles of size over a broader range. Okay, so it's basically containing varieties of particles. So that means you can say that the given soil sample is well graded. Now if this is not the case, so for poorly graded, you will be having a curve something like this. Okay, so if I draw it for poorly graded, then the soil is deficient or has an excess particles or of a particular size, or we can say all the particles are basically having a same size. Okay, so the gradient will be very steep. This this is for poorly graded case. Only a particular size particle is basically present inside the soil sample. So this is for the case of poorly graded. Now for gap graded, a particular size or a range of size is basically missing in that soil. So this will be something like this. Okay, so as you can see, this range this range is basically missing from the soil sample. So that's why it is called gap graded. So in this way, you can make a comment only by observing the grain size distribution curve. However, to make a specific comment about the given soil sample, you have to go for the calculation of these two coefficients, that is the coefficient of uniformity and coefficient of curvature. And you have to check these two conditions, whether the cu value is greater than 6 or not, and the cc value is in between 1 and 3 or not. So based on these two conditions, you can say whether the soil is well graded or gap graded. Now for this problem, or for the given soil sample, since the cu value is greater than 6 and the cc value is in between 1 and 3, the given soil is obviously well graded. So therefore this option is correct. So option 1 is correct. Okay, so according to the coefficient of curvature and coefficient of uniformity, the soil can be classified as well graded. So option 1 is the correct answer. Okay, so so far we have addressed the two questions which are framed in the last class. Now we'll go for the second problem. So the second problem is about the Atterberg limit test were conducted on the soil sample given in problem 1. That is on the same soil. Okay, we are dealing with the same soil. For liquid limit, the data set obtained for the soil is given in table 4. The plastic limit for the soil is 23. Assume the soil to be fully saturated at liquid limit and plastic limit. If the oven dried remolded soil of 250 cc volume kept for 24 hours in oven weighs 595 gram, what is the shrinkage limit of the given soil? That means you have to determine the shrinkage limit of the given soil, where the plastic limit and the liquid limit of the soil are given. Okay, so plastic limit that is given directly for this problem. However, the liquid limit that is not given directly, anyhow you can obtain or get this liquid limit from the data which are given to this problem. Okay, so that means number of flow versus water content. Now before determining all these limits, we'll have a quick look on this aspect, that is what is Atterberg limits. Okay, so Atterberg limits are this nothing but plastic, liquid, plastic and the shrinkage. So liquid limit is the water content at which a soil is practically in a liquid state but has infinite small resistance against flow. So this is taken from the lecture content itself. Okay, so liquid limit is defined as the water content at which a group carved in a pad of soil by a grooving tool of standard dimensions will flow together for a distance of 13 mm under the impact of 25 blows in a standard liquid limit device. So if you perform the liquid limit test and if you obtain the test data, then from this data you can get the liquid limit corresponding to the water content corresponding the impact of 25 blows in a standard liquid limit device. So this is the recommendation. Okay, so this is the IS code recommendation. So liquid limit is defined as the water content at which a groove cut in a pat of soil by a grooving tool of standard dimensions will flow together for a distance of 13 mm under the impact of 25 blows in a standard liquid limit device. Okay, and what is plastic limit? Plastic limit is defined as the water content at which a soil would just begin to crumble when rolled into a thread of approximately 3 mm diameter. Though this is not needed because the plastic limit of the soil is directly given, okay, to us. And shrinkage limit, this is the maximum water content at which a decrease in water content does not cause any decrease in the volume of soil mass. So these are the definitions of Atterberg limits. Now we'll calculate the limits one by one. So first of all, the plastic limit, that is WP. So this is given as 23. And the WL, in order to determine the WL, that is the liquid limit, first you have to draw this data, that is number of flow versus water content. So first you have to draw the flow curve. Now what is flow curve? Flow curve, this is the relationship between water content and number of flow. The curve which is obtained by joining the data in the water content versus number of flow plot. Okay, so this is the definition of flow curve. So these are the data. So these data are nothing but given to this problem, that is 55%, the number of flow corresponding to 55%, the number of flow corresponding to a water content of 55% is 8. Then number of flow corresponding to water content of 42% is 13. So in this way, number of flow corresponding to a water content of 20% is 32. So all these data are basically plotted in this graph, and these data points can be joined by a straight line, and this line is called flow curve. Okay, and please keep in mind this plot is again semi-logarithmic in nature. So y-axis is in arithmetic scale and the x-axis is in logarithmic scale. Okay, so x-axis represents the number of flow and y-axis represents the water content. Now how you can determine the liquid limit from this flow curve? So liquid limit can be determined from this flow curve as follows. Okay, so the water content corresponding to a number of flow of 25 will give you the plastic limit. So this is the 25 number of flow. This is 10, this is 20, this is 30. So 25 approximately you can take it here. Okay, and if you draw a vertical line, so it will intersect the flow curve at this point, and the coordinate of this point will give you the liquid limit, so approximately 27. That means WL, so this is 27. So WP, that is the plastic limit, is given as 23%, and the liquid limit which we have determined from the given data is 27%. Okay, now we'll cross check the classification, the soil classification which we have done in the first problem, because we mentioned earlier that for a specific classification or a more accurate classification, we have to consider the location of the soil in the plasticity chart, whether it is plotted above a line or below a line, because the fine content in that problem was more than 12%. Okay, though we have classified the soil sample in that problem approximately as 80%, that will re-cross check, okay, or re-verify. So this is the plasticity chart. In plasticity chart, So in the y-axis, you will be having plasticity index, IP, and in the uh, x-axis, you will be having liquid limit. Now, the plasticity index is defined by the range of water content over which the soil will be in the plastic state. That means IP, this is the difference between WL minus WP. Now, what is the WL for the given soil sample? WL is 27 and WP is 23. That means the plasticity index is 4. And this line, the line which is basically plotted in black solid, okay? So, this is a solid line and is having a color of black. So, this line is called A line. Now, this A line is having an equation. So, IP, the equation of A line is IP equals to 0.73 WL minus 20. That means 0.73 WL is 27 minus 20. That means 0.73 into 7, so 5.11. So corresponding to a liquid limit of 27%, the plasticity index is 5.11, and here the plasticity index value is 4. That means it is plotted below the A line. Okay, so this is 30 something here, you can say. Something here it is plotted. Okay, so it is plotted below A line. That again indicates the fine content is silty. Okay, so that means silty sand. So though this is the borderline case, okay, so means 4 in the sense, no, this is not borderline case, this is well below the borderline, that is borderline is 5.11 and the current value is 4. Okay, so that means below 5.1, that is below 5, the A line. Okay, so the soil is plotted below the A line, so that means the fine content is silty in nature, and as a whole we can classify the soil sample as silty sand, which we have done, or which we have classified earlier. Okay, so that means the earlier classification was correct. So that was a check whether we have done it correctly or not, and we can conclude okay, it was correct. Now we'll see how we can determine the shrinkage limit by utilizing the data of problem 2. So for determining shrinkage limit, we have first obtained the plastic liquid limit and the plastic limit. So plastic limit is given as 23%, and the liquid limit, which we have determined by drawing or by plotting the water content data, the water content versus number of flow data, and we have obtained the flow curve. Now in this flow curve, the water content corresponding to a number of flow 25, which we have determined as 27. Okay, so from this flow curve, the water content corresponding to 25 number of flow will give you the liquid limit, and that is 27%. Now what we'll see, will basically have an idea about the volume change versus water content, because this is very much needed before determining the, this idea is very much needed before determining the shrinkage limit of the given soil. So first of all, if you have a soil and if you mix water, sufficient water to this soil, so you will get, or you will end up with a suspension, and in that case the soil suspension can easily flow without giving any resistance. So that means the soil sample is in the liquid state. Now if you try to decrease the water content gradually, then what you will see? So suppose this is the liquid state where the soil suspension can easily flow without getting any resistance, means sufficient water is there. Okay, the water content is too high. Now if you try to reduce the water content of the suspension, then what will happen? The volume will accordingly decrease. Okay, the volume will decrease, and there is a distinction, or there is a borderline where the soil basically enters into a plastic state from liquid state. Now what does it indicate by plastic state? Plastic state indicates that it's a state of the soil, it's the consistency of a soil where the soil can be deformed into different shapes without fracturing the, without any fracture or any rupture. Okay, so that state is designated by plastic state. And the borderline water content means, as we have mentioned or defined earlier, that the plastic limit is defined as the water content at which the soil would just, the liquid limit is the water content that is the borderline between these two states, that is liquid state and the plastic state. Okay, so first let me plot the variation of volume with water content. So these are the different states of a soil: liquid state, plastic state, semi-solid, and finally solid. Okay, so when the water content is too high, that is the soil will basically behave as a liquid. So this is called liquid state. Plastic, where the soil can be deformed into different shapes without any rupture. Then again, if you decrease the water content, it will enter into the state of semi-solid. And finally, if you further decrease the water content, then it will enter into the state of solid. Now this distinction or this borderline between different states, okay, means the borderline water content between liquid state and the plastic state, this is called liquid limit of the soil. So this borderline water content between the liquid state and the plastic state, this is called liquid limit. Similarly, the water content between plastic state and the semi-solid state, this is called plasticity limit or plastic limit. And the water content between solid state and semi-solid state, this is called shrinkage limit. So these are the three Atterberg limits which define the borderline between different states of a soil. So the borderline between liquid and plastic state, this is called liquid limit. Plastic and semi-solid, okay, so the water content at which a soil enters into semi-solid state from the plastic state, that is called plastic limit. And the maximum water content, so beyond which there is no change in the volume, that is called shrinkage limit. Okay, so these are the three Atterberg limits which you can get from this volume versus water content plot. So if you decrease the water content, so the soil consistency will change from liquids to plastic, then semi-solid and solid state, and accordingly you will be getting the liquid, plastic and shrinkage limit. Now in this problem, liquid limit and plastic limit are known to you. What you have to do, you have to basically calculate the shrinkage limit of the soil, and that we'll see how we can calculate the shrinkage limit of the soil. Okay, so before that, we'll basically plot the three-phase diagram of a soil sample. So again, we'll go back to the problem statement, and we can observe that there is a explicit statement in the problem that assume the soil to be fully saturated at liquid limit and plastic limit. That means whatever void spaces are available inside the soil matrix that are fully filled by water only. No air is present inside the soil pores or soil voids. The soil voids are completely filled with water. No air is present in the soil voids. That is the physical significance of this statement, that assume the soil to be fully saturated at liquid limit and plastic limit. Now we'll have a brief understanding of the three-phase relationship or three-phase diagram of the soil sample. Now obviously this three-phase term will not be correct here, because since the soil sample is saturated, we will be having only solid and the water content. Okay, so inside a soil mass there will be only two constituents. The first one is solid and the second one is water. So that means the three-phase system is reduced to a two-phase system due to the full saturation or complete saturation. So this is the three-phase diagram when the soil sample is at liquid limit. Okay, so this is the solid part. So this is the solid part and this is water. And suppose that the soil sample is having a total volume V1. Now consider the case of plastic limit. Now what is happened here? So in plastic limit, the water content is nothing but the plastic limit. and it is lesser than the liquid limit, that we know. And what is happened in the total volume of the sample? The volume is now reduced compared to the volume at liquid limit. So at liquid limit, if the volume is V1, so in this case, you will be having a volume V2 which is lesser than V1. So with a decrease in the water content, so with a decrease in the water content, your volume is also reduced, and that is pretty much clear from this graph. Okay, so as you go on decreasing the water content, your volume is also decreasing. Now we'll consider, okay, and please keep in mind this reduction in volume is only due to reduction in the volume of water, because solid content cannot change. Okay, so whatever volume of solid is present, that will remain constant irrespective of these limits: liquid limit, plastic limit, shrinkage limit. Okay, so that will not change. Only the water, the volume of water is basically changing inside the voids, and that will be reflected in the total volume of the soil sample. So this is the solid content, or this is the volume of solid which is remain constant, and this is the volume of water, so it is now reduced as compared to the volume at liquid limit. Okay, now we'll see the two-phase diagram at shrinkage limit. So what will happen? So in this case, so this is the solid and this is water. So in this state, so since we are decreasing the water content further, W equals to WS, the volume will also be reducing. Okay, so suppose the volume is V3, so this is less than V2 and V2 is less than V1, so it's basically decreasing in a monotonic fashion. Now if we further reduce the water content, means beyond shrinkage limit, what will happen? Any idea? If we reduce the water content beyond shrinkage limit, then what will happen? The volume of the soil sample will now remain constant. However, the water inside the pores will be replaced by air, and the soil sample begins to dry at the surface, and the color of the soil sample also changes. So these are the observations you can have if you reduce the water content beyond shrinkage limit. Okay, so this is the solid. Now this water will be replaced by air. So this is for water content less than shrinkage limit, and in terms of volume, V3 equals to V4. Suppose the volume at this state is V4, then this V4 and V3 will be same. Now indirectly we can say, since there is no change in the total volume of the soil sample, so there will be no change in the void ratio. Yes or no? Can we make this statement? If there is no change in the total volume of the soil sample, then there should not be or would not be any change in the void ratio of that soil. Is it correct? Now, what is the definition? Tell me, what is the definition of void ratio? So, void ratio, this is nothing but the ratio of VB upon VS. What is VV? VV is the volume of voids, and what is VS? This is the volume of solids. Now at any condition, the volume of solids is not changing. And what's about VB? This is also not changing, because only the water inside the voids are replaced or is replaced by air. So since there is no change in volume, that means there is no change in volume of voids and volume of solids. There is no question about the change in volume in of solids. Okay, so that means this ratio would not change. So void ratio will also remain constant. So void ratio will not change. So therefore, the behavior of void ratio with water content, we can draw an analogy between the variation of volume versus water content and the void ratio versus water content. So somehow we are getting a similar kind of behavior. Okay, so the y-axis, if we consider void ratio, so we can expect a similar kind of behavior as we are getting in the case of volume versus water content. So if you decrease the water content of a soil sample, there will be a decrease in the void ratio, however, up to the shrinkage limit of the soil sample. Beyond that, there will be no change in the void ratio. And it's very essential to note that up to shrinkage limit, the soil is under full saturation. However, once the soils enters into the state of solid, means beyond shrinkage limit, the soil sample would be no more in the fully saturated state. So the soil sample would become partially saturated or become dry. Okay, so the soil sample become dry. So that's why I hope in the previous class we have also noted this kind of behavior, that this saturation, full saturation is valid up to the shrinkage limit. Beyond that, the soil sample begins to dry. Okay, now what we will do? So we have an understanding of the behavior of void ratio versus this water content. Now since we know the void ratio at all the stages, okay, so we know the void ratio at all the stages. How we know? Because for full saturation, this is the relationship, na? W GS equals to AC. Now for full saturation, S becomes 1. So therefore you can write E equals to WGS. Now, as you know, the liquid limit and plastic limit of the soil sample and the specific gravity of soil solids, you can easily calculate the void ratio corresponding to these two states. That means plastic and liquid limit. So your GS value is 2.67. Okay, so this is given in the problem statement, and WL is 0.27. It will give you the void ratio at liquid limit as 0.27 into 2.67. That means 0.72, and WP equals to 0.23. So it will give you the EP, that is the void ratio corresponding to plastic limit, as 0.23 into 2.67. That means 0.61. So you know the liquid limit and corresponding void ratio, plastic limit and the corresponding void ratio of the soil. Again, you know the void ratio corresponding to the dye strength. How you know? Because you know the volume of the dry soil sample and the weight of the dry soil sample. So gamma dry you can calculate by WD divided by V. So in this way, that is, so instead of gamma, can rho D. Okay, so density. So dry density is nothing but 595 gram divided by 250. That means 2 point, I think 2.38 gram per cc. Now, if this is the dry density of the soil, then there is a relationship between dry density and void ratio of the soil sample, corresponding void ratio. That is nothing but GS rho T is basically GS rho W by 1 plus ET. Okay, so ET you can calculate as GS rho W by rho D minus 1. That means 2.67 into 1 divided by 2.38 minus 1. That means 0.112. Okay, 2.67 divided by 2.38 minus 1 means 0.122. And this void ratio is not changing over the solid state. Okay, so this is the dry void ratio, or void ratio corresponding to the dry state, you can say ED. And what is the value? The value is 0.112. That means indirectly you know the void ratio corresponding to the shrinkage limit of the soil sample. And what is that? That is 0.112, because ED is not changing over the solid state like the volume of the soil. As the volume of the soil is not changing over the solid state, similarly the void ratio of the soil is not changing over the solid state. So that means you can calculate the water content corresponding to this void ratio. So ED is your 0.112. Then we can determine the value of WS from an extrapolation of these two data. Suppose, let me redraw the curve here. So this is water content, and this is void ratio, and the behavior is like that. So this is WL, this is WP, this is WS. Okay, so this is EL, this is EP, this is ED. So these two data points you know, and this point you know partially because you know the ED. So you can easily calculate the WS value. Okay, so by extrapolating these two data, data 1 and data 2, you can obtain the data at point 3. So this ED, this WS, you can calculate in this fashion. So it will be 0.27 minus, this is the gradient of the line, straight line, 0.27 minus 0.23 divided by WL minus WP, EL minus CP, that means 0.72 minus 0.61 multiplied by 0.72 minus 0. So that will give you, I hope, 0.27 minus 0.23 divided by 0.72 minus 0.61. Okay, this is not 0.112. So this is 0.122, I have. 0.122. Please correct this value here. So this is 0.122. So 0.0525. 0. Means 5.25%. And this is the answer. So in this way, you can determine the shrinkage limit of the given soil sample, where the plastic limit and liquid limit are known to you, and at the same time, the void ratio corresponding to the dry state of the soil sample is also known to you. Okay, so I hope this is fine with all of you. Now we'll proceed further. So we'll take this problem 3. So in problem 3, a fine-grained soil is found to be plastic in the water content range of 26% to 48%. As per Indian standard classification system, the soil is classified as. And this question was asked in GATE examination 2016. Okay, so you are given a fine-grained soil, and which is found to be plastic in the water content range of 26% to 48%, and you have to identify, or you have to classify the soil sample as per the Indian standard classification system. So this is the question. Now what we will do first? So it's a very simplified version. Why? Because here you need not to consider the sieve analysis or the hydrometer analysis data, because in this problem it's given in a very straightforward manner that the soil sample is fine grained. So you need not to bother about the sieve analysis and the hydrometer analysis data, because that are required only to classify, or only to get an idea about what type of soil is it at the very first check, or the very beginning. Because this Indian standard classification system begins with the check that whether the soil sample is coarse grained or fine grained in nature, and that is depending on the percentage of soil sample passing through 75 micron sieve or retained 75 micron sieve. So as we have done for problem 1. So that is not the case here. So in this problem, it's given very directly that the soil sample is fine grained. So that means you have to consider the plasticity characteristics of the soil to classify the soil sample further, because the coarse grained soil is classified depending on its grain and gradation characteristics, where a fine grained soil is classified based on its plasticity characteristics. Okay, so we'll first calculate the plasticity index. What is the plasticity index of the given soil sample? IP. And you know that this IP is nothing but WL minus WP. Now what is this liquid limit and plastic limit for the given soil sample? The liquid limit and plastic limit are nothing but 48% and 26%. Why? Because it's mentioned in the problem that in this water range, means 26 to 48%, the soil is found to be plastic. So these are the two borderlines. Okay. So borderline water contents. In between, the soil is found to be plastic. So WL is nothing but 48 and WP is nothing but 26. That means 22. This is the plasticity index of the soil sample, given soil sample. Now what we'll do? We'll calculate the IP value corresponding to A line. So corresponding to A line, the IP value is 0.73 into WL minus 20. 0.73 into 48 minus 20. So therefore 28 into 0.73, 20.44. Now if we draw this soil in the plasticity chart, so this is the plasticity chart. Sorry. So okay, now if we plot this soil in the plasticity chart, so obviously this soil will be plotted above a line since it's having a plasticity index of value 22, which is greater than the value 20.44 corresponding to the A line. So that means the soil is plotted above a line. So it's clay. Okay. So it's clay in nature. Now what will happen corresponding to the compressibility part? So since the water content range is in between 35% to 50%. So it's basically 26 to 48%. Okay. So as mentioned in the problem. So that means it indicates the soil is clay, intermediate compressible clay. Okay. So the soil is intermediate compressible clay. And the group symbol for this kind of soil is I. So it will be basically, it will fall in this range. Okay. So if I extend this line, So this is 35% water content, and this is 55%, and again this is plotted above a line, so 22. So somewhere here, okay. So it will basically it will be plotted above the A line, and the water content is in the range of 35 to 50%. So that's why the soil can be classified as CI. So this is the group symbol for the soil classification, CI, okay. And what is the physical significance of CI? So CI indicates clay with intermediate compressibility. The soil can be classified as C. Now we will take the next problem. The next problem is about sieve analysis. So a sieve analysis on a dry soil sample of mass 1000 gram showed that 980 gram and 270 gram of soil passed through 4.75 mm and 0.075 mm sieve respectively. The liquid limit and plastic limit of the soil fraction passing through 425 micron shapes are 40% and 80% respectively. The soil may be classified as. So this question was asked in GATE examination 2007, and in this question, first we have to determine the percentage finer corresponding to these two sieve sizes, okay, 4.75 and 0.075 mm. So here I can make a table like this, sieve size. Since our first check would be whether the soil is coarse grained or fine grained, okay. So for that we have to calculate the percentage finer corresponding to 4.75 and 0.075 mm respectively. So sieve size, then percentage finer. So sieve size is 4.75 and 0.075. Now for 4.75, 98 gram out of 980 gram out of 1000 gram was passing, okay. So percentage finer would be 980 divided by 1000, 200, 98, and that is for 75 micron sieve is 270. That is 27. Now what we can observe, that the soil is obviously coarse grained because more than 50% is retained on 75 micron sieve. Only 27% is passing through the 75 micron sieve. So almost 73% is basically retained on the 75 micron sieve, and it is more than 50%, say half of the total soil. So therefore it is coarse grained. Coarse grained. Again, out of this coarser fraction, 50% passes through 4.75 micron, 4.75 mm sieve. So only 2% is basically retained on 4.75 mm. So therefore it's sand. The soil is coarse grained, and further the soil is sand. Now we have to check what is the fine content. The fine content, so this is the first check, this is the second check, now this is the third check. So fine content is greater than 12%. This is 27. So therefore, now this problem becomes similar to the very first problem in this session, that is problem 1. Okay, so the soil is sand and it's having a fine content greater than 12%. Therefore, you have to go for the plasticity chart, whether the soil is plotted above a line or below a line. Now, how we can decide that? We can decide that on the basis of plasticity index of the soil. So WL is 40% and WP is 18%. So IP would be WL minus WP, that is 40 minus 18, 22, and from A line this IP would become 0.73 WL minus 20, that is 0.73 into 40 minus 20. So 14.6. So it's plotted, the soil is plotted above A line. Since it's plotted above a line, it means the fine content is clay in nature. So we can classify the soil sample as clay sand. And the group symbol for this classification would be SC. Okay, so this is the answer. So for this problem, first of all, we have determined whether the soil is coarse grained or fine grained, and we can see the soil is coarse grained because 50% of the total soil is basically retained on 0.075 millimeter sieve, and then we have identified whether the soil is sand or gravel, and we can see the soil is sand because 50% of the coarser fraction is basically passing through 4.7 mm sieve. And for the third check, we have determined whether the fine content is less than 5% or in between 5 to 12% or greater than 12%. And as we can see, the fine content for the given problem is more than 12%. So therefore, we have to locate the soil sample with respect to the A line. And as you can see, the soil is basically plotted above the A line. So therefore, the fine content is clay in nature. So as a whole, we can classify the soil as clay sand, and the group symbol for this type of classification is SC, where the prefix S indicates sand and the C indicates clay. Okay, now we'll proceed for the last problem, that is problem 5. The clay mineral whose structural units are held together by potassium bond. So 4 options are given: illite, kaolinite, montmorillonite, and none of the above. So to answer this question, we have to first have a brief idea about the atomic structure of these clay minerals. Okay, so we'll see it one by one. So for illite, okay, we'll start with the kaolinite. Okay, so since this is a 1:1 mineral. Why 1:1? Because the basic structure is one silica seed is basically embedded in one alumina seed. So that's why it's called the kaolinite, 1:1 mineral. And the others two elite and montmorillonite, it is called 2:1 mineral. That is the basic structure. In the basic structure, there is one silica sheet and two aluminum sheet. Okay, so we'll see one by one how the atomic structure looks like for this kind of clay minerals. So for kaolinite, okay, and it's repeating in both the direction. And this interlayer between these two structure, this is held together by hydrogen bond. Whereas for montmorillonite, the structure would look like this. Two silica sheet and one gibbsite. Okay, so I am using the abbreviated form. And this interlayer, these two structural units are held together by poor van der Waals force. And for elite, it's again a 2:1 clay mineral. Means the basic structural unit looks same as in the case of montmorillonite. However, there is a major difference in the bonding between two structural units. Okay, so in contrast to the montmorillonite clay mineral, the bonding in the case of elite is by potassium ions. Okay, so in the montmorillonite clay mineral, the structural units are held together by poor van der Waals force, whereas in the case of ylite, the structural units are held together by potassium bond. So that's why, considering this structure, we can answer this question as that the clay mineral whose structural units are held together by potassium bond is nothing but ylite. So option 1 is correct. This is the correct answer. Okay, so this was for today's session. Now we'll take one homework problem and we'll end this session here. So this is the homework problem. So data from sieve analysis conducted on a given sample of soil showed that 67% of the particles passed through 75 micron IS sieve. The liquid limit and plastic limit of the final fraction was found to be 45 and 33% respectively. The group symbol of the given soil as per IS 1498-1970 is. So again, in this problem, we have to classify the soil sample based on the given data, and this question was asked in GATE examination 2002. So I would like to request all of you, so please try to give an attempt to solve this problem and let me know if you face any difficulties in the next session. Okay, so these are the details about the upcoming sessions. That is, the next session will be held on February 9th, that is on Friday from 6 p.m. to 8 p.m. and that will be taken by Mr. Ashish Choudhury, and we'll again meet on next Sunday, that is on 11th February at 5 p.m. Okay, so at last we can summarize the session like this, that in this session we have mostly learned how to classify a given soil sample given the sieve analysis or hydrometer analysis data, or the plastic limit, liquid limit, and the shrinkage limit test data. Those shrinkage limit is not needed at all to classify the soil sample. So how we can classify a given soil sample based on the given data, that we have learned from this specific way. So this is the summary of this session. Okay, so now I will wait for a few minutes. So if you have any questions or you need further clarifications, you can ask me. Otherwise I will stop this session here. So thank you for joining this session, and hope we'll meet again on next Sunday.